Well, welcome everybody to Math 103 review sessions. If you're here in the room, it's September 2006. As you know, if you're looking at this online, you may have come across it on Princeton page or on Princeton University press page. As I do these sessions, my focus is going to be obviously on Math 103, but I hope that it also proves useful to anyone who's following along online in the future. So as I work through all this stuff, I'll be following or referring to examples in what you guys know as Math 103 review notes. And if you haven't gotten your copy of that, go to room 106 in Fine Hall. But it will also become, next April, April 2007, a book called The Calculus Lifesaver. So when I refer to the book, for those in the room or following along this semester in 2006, it's the Math 103 Review Manual, and after that, it's the Calculus Lifesaver. Okay? So, in any case, these sessions are somewhat open-ended. I'm here to help you. Okay, you've got your regular classes. These are not a supplement. These are a supplement. These are not a substitute for your main classes. I'm very, very happy to take questions at any time. You can come and go as you please. You know, by the midterm, all these seats are going to be filled the night before the midterm, but, you know, this is a great time to really catch up, and you're doing the right thing by coming early and following along during the semester. Don't fall behind. Okay, so here's my general plan of attack. What I'd like to do is review the material. I'm going to go over all the stuff that you're doing in your regular class. It's not going to be everything in the book. It's not going to be everything even in your class, but I'm going to try to touch upon the most important things. So here's another disclaimer. So some of my methods, either what I show you on the board or in the book, are maybe different from what your professor has taught you. Okay, hopefully both methods are correct. And if you're in doubt, you should always check with your professor. You can say, hey, this is a different way to do it. I'd like to do that way. Is that okay? Most of the time, it's going to be okay. I've tried to be quite detailed and present solutions which I think will get you full points. But if in doubt, check with your professor. I'm not grading. I'm not grading your exams. I'm certainly not grading your exams. So, that's the basic spiel, introductory, as it were. About tonight's session, I'm going to do pre-calc. Okay? We're talking functions. I'm going to go over the background that you need of functions, and I'm going to spend quite a bit of time on trig, especially. So those are the two big ingredients that you really need before you even get started. And then next week, I'll start reviewing the material that you're already doing in class, which begins with limits. Okay? So that's the game plan. Now, these sessions are, despite the camera, despite the big auditorium here, the sessions are quite informal. So please ask questions. Come and go as you please. You don't have to stay the full 2 hours. You can come late. There's no such thing as being late. Just come, take what you need, and I hope it helps you. So, are there any questions before I begin? Of course.
Do you know anything about the old book and the new book?
The old book and the new book. Now, is this the old textbook or the old, as in Stein and Barcelos or Thomas? I know that there are some new editions of it, but I'm not quite sure what the differences are. So, okay. We have that it's... Okay. Did you all get a copy of the Math 103 review notes already? Okay, if you didn't, as I said, Fine Hall 106. They're advanced copies that the Math Department and Princeton University Press have graciously provided so that you have something to follow along, as I say, section 1.2. By the way, if you're watching this online, you do not need the book. I'm going to spell everything out. Obviously, if you have it, you can follow along. The two are designed to be independent, but they do work together. And of course, everyone here has no excuse since they're free. Okay, are there any other questions before I dig in? Remember, you can ask questions about the math along the way. I was just wondering if anyone had any general questions. Okay, well, let me start off by talking about functions. Okay, so as I say, this is all pre-calc, this is all review, but this is the fundamental, this is what you really need. And the main ingredient for calculus is functions. Okay, if you didn't have functions, you'd really be hard-pressed to do anything useful with calculus. So let's remind ourselves what a function actually is. It turns out it's not that easy to define a function. The best way that I know is to think of it as taking some objects that are in some sort of set or class or family. I think of it as like a soup. So this is going to be called the domain. You pick something in there and you hit it with a rule. And you get something from another soup. Different objects in this soup. That's called the codomain. Okay? All three of these things really together form the function. So you say a function is a rule, but technically it's not just the rule, it's also the domain and the codomain. Now most of the time, in fact probably all the time in this course, we're going to be dealing with the domain and the codomain essentially being either the whole real line or part of the real line. Okay? So I'm not going to be dealing with a soup. The soup is the real line. Okay. So everyone's favorite function, or my favorite function, at least at the moment, is f. Well, obviously, what is f? I said I've got to specify the domain. I'm going to say the domain is R. So R is the real line. It's the set of all real numbers. And I'm going to say the codomain is R. Cod is not fish. It is the codomain. And the rule I'm going to specify is f of x equals x squared. Okay, that's a perfectly nice function. What this means is you take something in R, so you take any real number, you hit it with the rule, which means that you're squaring, and you get back a real number, codomain. Okay, so that's a perfectly nice function. There's some other functions you could define. Consider this one. Let's let h of x be the number of legs that x has. Okay, so that's the rule. I should have said the domain R. Well, let's suppose the domain is just the set of animals. So I'm going to use a curly brace for sets here. Okay, the domain is the set of animals, but the codomain cannot be the same thing. In fact, the codomain will just say that this is equal to, I'll say it's equal to, say, non-negative integers. Now, you may not have come across the word non-negative before. The deal is that positive are positive numbers, non-negative is positive numbers, and 0. It's a very useful word, okay? So, non-negative integers. Okay, well, fair enough. It's h of a, say, horse. This can be interactive too. I know you guys can't talk out there, but online in the future, whenever you're watching this, but someone in the room can tell me what h of a horse is. Just shout it out. 4. Okay, so we started off with the horse, we hit it with the h rule, and we got back 4. Okay, so clearly you could get a lot of different non-negative integers. You could get 0. I guess a snail doesn't really have any legs. I'm not a biologist. Maybe 1 is pretty rare, but I'm sure, you know, there's some poor one-legged birds hopping around. You know, I doubt that h of anything is a billion. There's probably no animals with a billion legs. Although if you're watching this in the distant future, who knows, they may be genetically engineered something. In any case, that's the idea. Now, you've also heard of the range, right? So the range is part of the codomain. It could be all of it, but it actually consists of those elements in the codomain that you actually get from the rule. So I started alluding to this. Is a billion in the range of H? When I ask that question, I'm asking you, is there any animal that has a billion legs? So if you start with any animal and you hit it with H, do you get a billion? And the answer is probably no. But 4 is in the range of H. So what's H of a chair? Anyone tell me what H of a chair is? Who thinks it's 4? You can raise hands if you like. Okay. Who thinks it's not 4? Who doesn't think? Okay. Well, in any case, H of a chair is not 4. In fact, H of a chair is undefined, because chair is not in the domain. Right? I said the domain is animals, and by no stretch of my imagination, in any case, is a chair an animal. Anyway, this is a very gentle sort of introduction here. So, let's talk about how to find domains and ranges of functions then. We've decided that the range of H is sort of hard to find. How would you find the domain and the range of f here, this function? Well, you've got to ask yourself, what numbers can you square? Well, I've already given you the domain is R, so there's not really any question there. But what would the range be? For example, is 4 in the range? Yes, because 2 squared is 4. Minus 2 squared is also 4. How about negative 4? Is that in the range? No, because there's no number that you can square and get negative 4. Okay, so anyway. Oh, look at this. Precept starting. I don't think that applies to anyone here. Cool. Okay, before we talk about how to find domains and ranges, I need to tell you about this interval notation. Now, you've probably seen this before, so just to remind you, a lot of times we're going to be dealing with subsets of the real line. They might consist of numbers going from, say, 3 to 7, including everything in 3 but not 7. That's an example. Another way you can draw that is with a closed circle on one end and an open circle in another. So this is the set of all x's, so that 3 is less than or equal to x is strictly less than 7. It's really useful to be able to write that like this. Okay, so I've just sort of taken this notation here and written it like this. So this is another way of writing this that doesn't involve less than or equal signs, and it's much more compact. Okay, so I won't go through all of the examples because they're in section 1.1 in the book, but if you have something like this, all the numbers from minus 3 downwards, inclusive, that would be minus infinity up to minus 3 inclusive. By the way, infinity and minus infinity are not numbers. They're not numbers. So you cannot have, as far as we're concerned anyway, a closed bracket around minus infinity or infinity. It's more advanced mathematics where that comes in, so we're not going to worry about that in this course. Okay, so suppose I just say, and this is going to be a different f, you've got to get really good at changing letters. Functions are not always going to be f, sometimes they'll be h, g. The variable doesn't always have to be x. Okay, so these variables are going to change around, but often the function is going to be f of x. And here's the function I have in mind. So this is in section 1.1.2, I believe. Okay? So it's the base 10 logarithm of x plus 8 times square root quantity 26 minus 2x. X minus 2 times x plus 19. Okay, so I say that's a function, but I didn't tell you what the domain is, and I didn't tell you what the codomain is. Well, as far as I'm concerned, unless I state otherwise, the codomain is always going to be R. Okay, the range may not be all, but the codomain is always just going to be real numbers in this course. Okay, what's the domain? The domain is going to be as much of R as possible, unless I specify otherwise. Okay, so here's what we're dealing with. I give you this function. I didn't tell you what the domain is. So it's implicit that you're going to take as much of this as possible. So what is possible? Well, there's a lot of functions out there. We'll be looking at the main ingredients list of functions a little bit later on. But here are 3 really useful rules about a screw-up. What screws up a domain? Or a potential candidate for the domain. So there's basically 3 common problems that can happen. So denominator equals 0. If the denominator is 0 in a fraction, that's bad. That also includes something like tan of 90 degrees. It doesn't look like it's a fraction, but if you actually remember that it's more like sine 90 over cosine. No, that doesn't work. Okay, so tan of 90 degrees is undefined. 90 degrees is not in the domain of tan. I'm going to be switching to radians in about 45 minutes, but for the moment I'll stick with degrees. Okay, so denominator equals 0 is bad. Okay, another possibility is you cannot take the square root of a negative number. That's bad. And the third one, no, it's not square root at all. It's logarithm. You cannot take the logarithm of a negative number or 0. You can't take log of 0. And that's true for any base. Doesn't matter what the base is. No logs of 0, no log of negative numbers. Doesn't make sense. We'll be looking a lot at logs in a few weeks' time. Or if you're watching online, a few links' time or something like that. Hopefully the links will all be labeled very clearly and you'll be able to see which video refers to logarithms. Okay, so in our example here, we've got all these factors. If an x is going to be in the domain, we've got to make sure that every factor is cool. We can't have any of these problems here. So for our f, well, let's start off with square root of 26 minus 2x piece. Okay, well, for that to be defined, 26 minus 2x has to be greater than or equal to 0, because you're not allowed to take the square root of a negative number. Okay, so this means that x, well, let's see, 2x has to be less than 26, so x has to be less than or equal to 13. Okay, so if we start sketching out what's allowed, we've already eliminated everything to the right of 13. Okay. So what about the log piece? So here, x plus 8 has to be strictly greater than 0. So notice the difference between the square root and the logarithm is that here we have a greater than or equal to for the square root, but a greater than for the logarithm. Anyway, this says that x has to be greater than negative 8. So actually, we can throw negative 8 on here, and we'll put an open circle there, so we're not even allowed negative 8. And on the denominator, x minus 2 piece means that x can't be equal to 2, so we'd better cut out and exclude 2 here. And also, what about the x plus 19 piece? Well, that means x cannot equal negative 19, but that was no problem because we knew it had to be greater than negative 8 anyway. Okay? So basically that contributes nothing. So the overall set that could possibly be the domain is minus 8 all the way up to 13, and I put a backslash. This is useful. I'm not going to use the backslash very often, but it's good to know this means not including. So it's all the numbers between -8 and 13, including 13, but not -8, and also eliminate 2. Okay? As I said, we're starting pretty gently, but this is pre-calc review. So are there any questions about that example or anything I've said so far? All right. So here's a question. G of x is x squared, domain is R. H of x equals x squared, domain, say, let's do -2 to 1. Are they the same function? Who thinks they're function? They're different functions. The rest of you, what do you think? Come on, I want to see some opinion here. Who thinks they're the same function? Who thinks they're different functions? Well, as it turns out, they can't be the same. They have different domains. Okay? They have different graphs as well. If you graph G, you get the whole thing. If you graph H, you only go from -2 to 1, and you just get this static little part of the graph. Okay? So, we're going to say that that right-hand function is formed by restricting the domain. So H comes from G by restricting the domain to -2, 1 in this case. Okay, so how are we going to find the range of these two functions? The best way is probably from the graph. So to find the range, draw a graph. What you'd like to do is imagine there's some sort of bright lights out here, and what you're interested in is the place that is shadowed out. So this is shadowed. This is the range. It doesn't get the light. That's one little way of looking at it. Here, you have the lights coming from both sides. This part's shadowed out from this, and down here we're only shadowed out there, but it's the total shadow that we care about. So how high is this shadow? Well, it goes from 0 to 4. The fact that on the right-hand side it only gets us down to 1, it doesn't matter. So the range in this case, well, let me just put it down here. So, well, range of G is 0, infinity, whereas the range of H is 0 to 4 inclusive. Okay. So I want to talk more about restricting the domain. And here we're getting into some pre-calc that maybe isn't quite as solid. It's not really talked about that much, about inverse functions. I need to talk about that. So first of all, if you have a function, its graph looks something like this. Is this the graph of a function? No, because, remember, we got one rule that takes it something in the domain and changes it to something in the codomain. So you don't get a different thing every time. You always get the same thing when you apply it to the same number. So if I pick a number here, what's the function value? Is it this, or is it this height? That's what the graph is, after all. What this means is if this is x, then this height here is f of x. That's what we mean by the graph. The y-coordinates are the f of x's, the function values. That's why we write y equals f of x. So in this particular case here, you wouldn't know which function value to take. So this is the vertical line test. I'm not going to harp on it very much. Basically, if you can draw a vertical line and it intersects your function or your graph more than once, it is in fact not a function. So if you did have a circle You'd actually turn it into a function by maybe just taking the top half, or you could take the bottom half, or you could mix and match if you felt in the mood. You could just sort of, well, this is a pretty lousy circle here. So the main point is I've tried to design it so that we never have 2 points in a vertical line. Okay, so let's talk about inverse functions a little bit. So this is in section 1.2, moved on to. The trig's going to be at around 8:30, by the way, so if you feel like you know all the functions and you want to get some fresh air, then that's cool. We're online, I guess you can skip ahead to halfway through. But I got a few more things to say about functions first. Okay. Here's what we'd like to do. We'd like to define an inverse function. That's like an undo operation. Okay, so if 2 squared is 4, then the square root of 4 is 2. So the square root is the inverse of the square. It's like the undo button, as I said. So here's the problem. The square root of 4 is 2, sure. But what's minus 2 squared? It's also 4. So how do you know which square root to take? So this is why you've got to do something called restricting the domain. So here's the basic idea. Suppose you have a function. What you'd like is you'd like a horizontal line test to apply. You'd like for only 1 point to be at that height. So this is no good. So how do we restrict the domain here to make sure that the horizontal line test works? Well, you pretty much have to throw half of it away. You could choose the right half or you could choose the left half. Let's just throw away the left half. So I'll make like a ghostly half there of the parabola. So I've restricted the domain. Okay, now there's something really useful here. Suppose we have something like f of x equals y. And you've picked a certain x. Well, you get a y. How many other x's satisfy the same equation? The answer is there's only that one x that works. See here, f of 2 is 4, and f of minus 2 is 4. So guess what? If I write down the equation f of x equals 4, I don't know which x to pick. There's 2 of them. It's okay if there's none, but we can't deal with more than one. Okay, so if this is true, if there's only one solution for every x and y, or at least for every y, we can define a new function by writing f inverse of y equals x. And we're going to be coming back in a few weeks to inverse functions and trying to do derivatives of them and all this sort of funky calculus stuff. So it's really good to try to get a grip on this soon. So, okay, we've got this idea of needing to take the inverse here. This f inverse is actually a new function. Okay, so the deal with it is it needs a domain. And the domain is actually the range of the original function. Maybe I'll just put domain of f inverse. And the range of f inverse is the domain of f. So it seems a little bit weird, but actually it's not so weird because the way to find the inverse function, or at least on the graph of it, is the reflection in this mirror. Think of it as a mirror. It's like a two-sided mirror, y equals x, the straight line with slope 1. So if you do actually reflect this, you'll get the inverse function. So here's y equals f of x. and here is y is f inverse of x. And let's say this happens to intersect at 1, 1. All right. So what is the domain of this function? We've restricted it to 0, infinity, so actually that becomes the range of the inverse function. Now, this isn't a fantastic example because it happens to have the same domain and range. But consider the negative square root. If you restrict it to negative infinity up to 0, then the inverse, you've got to reflect it in this line here. It'll look like that. So the domain of the inverse is actually positive numbers, which is the same as the range of the original function. But the range of the inverse is negative numbers, which is the same as the domain of the original function. So they switch around. And now you know how to draw the graph. Okay? So, here's a question. Suppose you have a function f. Suppose you have an f and you have an inverse f. Inverse. F to the minus 1, it doesn't really mean you're taking a minus 1 power. It means you're taking the inverse. So suppose you have that. So my question is it true that f of f inverse of x equals x? And is it true that f inverse of f of x equals x? Are these true? Well, you'd think they should be true because they're supposed to be undo operations. They're supposed to undo each other. Actually, I don't have time to really go into this, but if this does exist, then basically the inverse of the inverse, you get back the original function. Right? So they undo each other. So this is going to come back to bite us when we do some inverse trig stuff a little later if we don't understand it properly. Here's what the first equation would say in the case of f of x equals x squared. So if f of x equals x squared, f inverse of x is the square root of x. Okay? Watch me closely here. I'm going to say something that's not quite true, and I want to see if you can spot it. F of f inverse of x says, first of all, we're going to take f of the square root of x, right? Because that's f inverse of x, which means we're going to square the square root of x, and you get x. So yes, we've hit it with the square root, then we undid it with the square. On the other hand, if we do it this order, then we're taking the inverse of x squared, which means we're taking the square root of x squared. Is that x? Is that x? Who thinks it's x? Who thinks it's not always x? Okay. Well, it's not always x. In fact, it's the absolute value of x. If you don't believe me, put x equals, say, minus 3. Minus 3 squared is 9, but when you take the square root, you get 3. This square root means positive square root. Always. Whenever you write that radical sign, you mean it's a positive number. So, in fact, this is not always equal to x. It's not always equal to x for negative numbers. Okay, so where did I go wrong? I mean, these statements are true. What's the real problem here? Can anyone see it? I won't keep you in suspense, but if anyone has a good idea of what I did wrong, right at the beginning, actually, the top right hand, the top line there. Well, basically, the problem is, if f of x equals x squared, it doesn't have an inverse, right? It doesn't obey that horizontal line test. Okay, the only way x squared can have an inverse is if you throw away part of the domain. You have to do either that or some weird hybrid combination where you take a little piece of the right curve and then a little non-overlapping piece of the left curve so that the vertical, so that no horizontal line goes through it more than once. So basically, the problem is that this is no good. We should have restricted the domain first. We should have said, no, x has to be positive or else we can't even write that. And in that case, this would all make sense. Well, that always makes sense. This one would make sense because x would be positive and the absolute value of it would just be x itself. So basically, this is always true, at least if x is in the domain of the inverse. Okay, I mean, part of the problem here is that if x is negative, you can't even hit it with the square root first. It's just not allowed. So that's always true if x is in the domain, and this is only true if x is in the restricted domain Anyway, these are quite subtle points, and we'll be revisiting them when we do inverse trig. Okay. So are there any questions about inverse functions? If you have a question, you can just shout it out. I know I'm all the way up here, and I've got the microphone and all that, but please, feel free to just shout out a question. Don't stand on ceremony here. In fact, I didn't even introduce myself. I know a lot of you came in a little later, and as I said, there's no late here. You can come and go as you please, but now that we're nicely into the middle of the first lecture, my name is Adrian Banner. If you're wondering about the accent, it is from Sydney, Australia, with about 9 years of New Jersey on top of that. So, in any case, I want to move on to say a few little things about composition of functions. If you've done any calculus before or looked ahead, you will have seen the chain rule. It's one of the first things we'll see after we do derivatives. And so that involves something called composition of functions. And rather than sort of get into it, I'll just give some examples, and these come from section 1.3 in the book. So suppose g of x is equal to 2 to the x. And again, I'm not saying what the domain is, but actually you can take 2 to any power, so the domain is all of r. The whole real line. H of x equals 5x to the 4th, ditto that, and j of x equals 2x minus 1. So again, you can hit the domain of all three of these is the whole real line. Okay, so what I want to do is form a new function, which I'm going to call f. And I'm going to write f as g OH OJ. So that's a little o, and it means compose with. Okay, so it's a little bit confusing because it's actually written left to right, but you've got to do it from right to left. What you're going to do is you're going to take some x, you're first going to hit it with j to change it to something else, then you're going to take that and hit it with h, and then you're going to take that and hit it with g. And it definitely matters which order you do it in. The order matters, so you have to work right from left. In fact, f of x, if this is how I'm defining f, then f of x is going to be g of h of j of x. And you've got to get the number of parentheses right. Actually, hopefully by the time you guys read this online, in the next example, the number of parentheses will have been fixed. But in your advanced copies here, I think I screwed up one of the parentheses. So anyway, never mind that. What is this? Well, first we take x and we hit it with j. So this is g of h of 2x minus 1, because that's what j is. So we've replaced x by 2x minus 1. Now when we're taking h of x, we're not doing h of x, we're doing h of 2x minus 1 quantity. So we've got to take, whenever we see x, we have to replace it by quantity 2x minus 1, and do not forget the parentheses. So I'm going to leave the g for the moment. H of 2x minus 1 will be 5 2x minus 1 quantity, all to the 4th. This just takes practice. I mean, you probably already can do it, but just make sure that you get the correct parentheses in there. Actually, for 2 to the x, we don't need parentheses, it's going to be 2 to the power 5, 2x minus 1, all to the 4th. The reason we don't need the parentheses around all this junk here is that we've already got a superscript. Sort of acts like its own little set of parentheses. Okay, so as I'm erasing all this, does anyone have any questions about that? If you do, don't wait for me, just shout it out. I've never taught in this room before. It's like a little stage. I feel like I should be singing something. But I will spare you and instead tell you that you sometimes have to reverse the operation. So here's what I have in mind. And again, this is in section 1.3. Suppose I let f of x be the rather nasty looking function 1 over tan 5 log base 2 x plus 3. Okay? Well, what I'd like to do is do the opposite of what I just did. Instead of taking with a few functions and making them into a new one, I'd like to take one function and bust it up into other functions. And this is a skill you absolutely have to have, whether or not you have it already. If you don't, you have to acquire it through practice. The idea is you try to zoom in on the x and say, what's the first thing you're doing to x? Well, the first thing you do in order to compute this is add 3. So let's suppose we let g of x equal x plus 3. Okay, then what's the next thing you do? Well, you take the log of it. So let me be consistent with my notation here. Yes, h is the next letter. We'll take the base 2 logarithm. Then what? Well, you multiply it by 5. So what we're going to do is we're going to let j of x be 5x. Now notice that I'm not letting it be 5 log 2 x plus 3. I'm just saying, what's the operation here? The operation is add 3, take the log, multiply by 5. Anyway, the next thing we're going to do is take the tangent. If we do g and then h and then j and then k, we get the denominator. So finally, we've got to take the reciprocal. So let m of x be 1 over x. And with this sort of atomic decomposition, I leave it to you to check that f is indeed m, ok, oj, oh, og. It's a bit complicated, but there you have it. So what this means is x, you hit it with g, then h, then j, then k, then m. And finally, you get what f would be if you just hit x with f directly. Okay? Now, there's not just one way to do this. I actually could have combined, for example, j and h. So if instead, suppose I let n of x just be 5 log x base 2. That's still a pretty simple thing to do. It's not quite as decomposed. But then, if I did that, I could combine the j and h steps into n. So here, n is itself the composition of, first of all, we're doing h, and then we're doing j. Okay, so again, I'm not really doing anything with this. I'm just saying you have to be able to do that, because soon we're going to be doing something with it. Okay, and it's really not anything other than if I asked you to calculate it. If I said, what's f of 1? You'd have to do 1 plus 3, and then you'd have to take the log. Even if you did it on the calculator, you'd still have to do something like this. I guess if you use a programmable calculator, you could type in the function and let it do the work. But let me just say something, at least to Math 103 students here, and maybe a general plea to those out on the net in the future, my future anyway. Basically, don't use calculators. Okay? I know you've used them a lot, probably, but just don't use them, because you can't use them, at least in Math 103, on any tests or exams. And so you've got to become quite good at dealing without them. But that being said, you rarely have to do any computations that would really benefit from a calculator other than, say, graphs and stuff like that, and you should know how to do that anyway. So I'm never going to be saying calculators much, and if I do, you can call shenanigan on me or something, right? So just don't use calculators. That's my advice. Okay, so basically that's all I want to say about composition. Are there any questions on that? Okay, practice. Now, there is one special composition I should mention. If you compose any function, fn is what I mean. I write fn, I mean function. With, say, g of x equals x minus a. So a is a fixed number. That's just a very simple function. You subtract a. The new function that you get, has a graph that's shifted over by a units to the right. So, for example, if you have to draw the graph, if f of x is, say, x minus 1 all squared. Well, if you think of this in the terms of composition, f is equal to, say, h of g, where g of x is this translation thing, this shift thing, and h of x is x squared. So if you think about it, what we're doing is taking away 1 and then squaring it. So the function is, it's just like x squared, but first of all, we're shifting it over by 1. So the graph of this, you don't even have to think about it. You don't have to expand it out. You don't have to do any of the whole junk on quadratics. You just take the regular x squared graph and you shift it over by 1. Okay, so that's the graph. Good. Okay, we better move right along. There's something quite important I have to talk about. Odd and even functions. Okay, this one comes up actually during this course a little bit, and you've got to get these notions in your head. Let's start off with what an even function is. So, an even function satisfies that equation. Actually, maybe I'd better write it like this. I'm going to switch it around. It has to satisfy f of minus x equals f of x for all x. At least all x in the domain of f. Okay, so what's that going to mean? What's that going to mean when we draw the graph? It'll mean it has a mirror symmetry. Around the y-axis. Why? Well, here's an x. There's the height. The height is, well, maybe I'll pick x out here. The height here is f of x, by definition. Minus x is on the other side of the mirror here. And what that equation is, it says it has the same height. Okay, so f of x is the same as f of minus x for all x. So that's the definition. I'll give some examples in a few seconds, but let me tell you first what an odd function is. Well, f of minus x is this time minus f of x for all x. At least all x in the domain. So the graph of such a function looks something like this. So it has a point symmetry, 180-degree point symmetry. At the origin. Okay, let's see why. Here's x. There's f of x. Well, at the other side here, at minus x, instead of going up to a height of f of x, we have to go to down a height of f of x. That puts us to minus f of x. And so if you think of this as a rigid sort of paperclip bent out into that shape. All you have to do is wiggle it around, and it will line up with this, and that tells you the other half of the graph. So this is going to be very useful when we do curve sketching, and we see, oh, this function is odd. We only have to sketch half of it, and then the other half you can just draw in by symmetry. Not every function is even or odd. Most functions are neither. Okay? So don't think that all functions are one of the two. That would be very nice, but it's just not true. In fact, you can see it just by drawing the graph of anything that doesn't have that sort of symmetry and still satisfies the vertical line test. That will be a function that's neither even nor odd. Any questions about that definition as I'm just finishing off this erasing? You're a quiet group, but that's cool. Okay, we better look at some examples. All right, here are three functions. Which ones are odd, even, or neither? Okay, so this is in section 1.4 of the book. Okay, so there's one function f. I'll just write down the other two. So it's 2x cubed plus x over 3x squared plus 5. And finally, h of x is 2x cubed plus x minus 1 over, again, 3x squared plus 5. All right, so we've got these three functions, and we want to know whether they're even or odd. Well, here's the technique. You plug in minus x instead of x. That doesn't look much like an x. There, plug in minus x instead of x. Okay, let's do it. F of minus x. So you've got to take, well, instead of x to the 6, we'll take negative x in parentheses. It's important to put the parentheses there, or else you'll screw the whole thing up. Same thing here with the x squared, negative x all squared plus 3. And if you simplify that, which you should do, you simply get 2x to the 6 minus 6x squared plus 3. Once you've simplified it as far as you can go, look at it and compare it to the original function. Hey, it's the same. The same as the original function, so f is even. If you're going to be really anal about it, you should say f is even instead of f of x is even. F is the function. F of x is what happens when you take x and hit it with the function. But I'm not going to be too particular about it. I'm just mentioning it's better to say f is even rather than f of x is even. By the way, notice how I use equal signs. Okay? You may be used to not writing equal signs between equal quantities. Okay, that might get you by in high school where you're basically trying to show that something equals something else. But in this course, we're going to have to sort of say this equals this. Now, stop, think about this. Okay, that equals this, and so on. So it's really important that you keep a chain of things that are actually equal to each other, joined by equal signs, regardless of whether they're on the same line or different lines. You need those equal signs. Okay, let's just do the others quickly. G of minus x is 2 quantity negative x all cubed plus quantity negative x. On the bottom, we have that. And if you expand it out, because it's odd powers on the top, the minus signs come out, but on the bottom, the square, again, looks like that. Now, you've got to take this simplified expression and compare it to the original one. What you want it to do is say, well, is it the same as the original? No. But is it the negative of it? Yes. Take out a factor of minus 1, or take out a minus sign if you prefer, and you will see it immediately. So there it is. that is minus g of x, so g is odd. And finally, very quickly, if we take our h of minus x, it's very similar to g, it's just that there's a minus 1 in there. How can that minus 1 make much of a difference? Well, it does. Here, you're going to get negative 2x cubed, negative x, or rather minus x, and then minus 1. Well, that's not the same as the original function. And even if you pull out a minus sign, you're going to get 2x cubed plus x plus 1 over 3x squared plus 5. That's not the negative of the original function. This plus 1 screws it all up. So h is neither even nor odd. Okay? Any questions about even and odd functions? Well, I have a few more things to say about functions. Not too many. We'll take a short break after I say a little bit more. If you guys feel like it, we could take a really short break if you just want me to keep going. But basically, what it's going to be, I'm going to tell you a bit about lines first, then I'll come back and tell you a little bit about common functions and trig functions especially. Okay, so just quickly whipping through section 1.5 of the book, I just want to remind you a few things about lines. If you have y equals mx plus b, this is called a linear function. It's actually, I haven't written it as a function. A linear function best would look something like this. Same thing. This is more evocative of the graph here, although you can think of y as a function of x too. Anyway, the graph looks like this. It has a slope m, and slopes are going to be really important. Derivatives have everything to do with slopes. The y-intercept is at b, which means that's the height there. So just to remind you, slope 0 means you're flat. The higher the slope is, the steeper it gets. And if the slope is negative, then it's actually going downhill. And I like to think of a little mountain climber climbing up. There's a better picture of that in the book. But if it's going uphill, then it's positive degree of difficulty. I'll be talking more about degrees of difficulty as it comes up. So the higher the slope, the harder it is to climb up. As it goes down, well, I guess if it's really steep, it might be hard to get down safely as a skier, but it's quite easy to get down. You just sort of roll down and probably die. But it's easier anyway. So in any case, that's the deal here with the picture. The things you really have to know. And here's the first time I'm going to use a box. I'm going to say the line through a point x0, y0 of slope m has equation y minus y naught is slope m times x minus x naught. And that is something you absolutely have to know. Really, really important. It's going to come up when I say, what is the equation of the tangent blah? You need to know that formula. It's just pre-calc as it comes, but yet, you know, it sort of gets neglected. So don't forget that. You've got to dredge that out. That's called the point-slope form. Okay, and just for a little example, e.g., so this is in section 1.5, as I said, line through negative 2, 5 of slope negative 3. So that's what we know about the line. We know it goes through negative 2, 5, which is up here, and we know its slope is negative 3. That's enough to tell us what the line is. All I do is I say y minus 5 equals that slope, negative 3, outside of x minus 2. Don't forget, minus becomes a plus. And if you simplify this out, you can make it into a more standard form by expanding it out and adding 5 to both sides, and you end up with y is minus 3x minus 1. And you can see the slope minus 3 there. That's a good reality check to make sure you didn't screw it up. The slope was supposed to be minus 3. there's one other little thing to say, and I'll just pop it down here. So the other thing to say is that the line through 2 points, forgive my bad spelling of through, x1, y1, and x2, y2 has slope rise over run, which is y2 minus y1 over x2 minus x1. That's not going to come up so much, so I won't put a box around it, but it's useful to know. So then you can use point slope form to find the equation. And I'm not going to do an example, but if you look in section 1.5 of the book, then, and just to remind you, that means when I say the book, I mean my free, for you guys, advanced copy, and for you guys, well, probably not free, but nevertheless, hopefully not too expensive, copy of either the Math 103 review notes or the Calculus Lifesaver, as it will be known in its final form. So basically, there's an example of how to use that. But this is the one you really have to know. Okay, well, let's just take a little bit of a breather, maybe just 5 minutes, enough time for me to erase some of these blackboards here and start off with a quick review of the common functions you need, especially trig functions. So most of it will be trig. Okay? So let's take a break. Right, the cameras aren't rolling. You don't want me to swear really quickly? Is that coming out okay on the tape? You can... All right, so let's continue with a little survey of common functions. Okay, this is going to be a pretty quick survey. So this is in section 1.6. Okay, think of this as your ingredients list. All the way through Math 103 and even Math 104, if you take it, the second half of the book, syllabus, we'll be dealing with pretty much the same roster of functions. And here's what they are. Okay, so polynomials, they're pretty common. In general, they look like this. And you're going to one day have to be able to write this out. So that's what they look like in general. You've seen plenty of examples, and we'll certainly see plenty of examples of these things. But it's useful to know that these ANs are called the coefficients. So AN through down to A0 are called the coefficients. And the highest non-zero power is called the degree of the polynomial. The whole term is called the leading term. Anyway, that's a really quick thing about polynomials, but I want to concentrate on degree 2 polynomials. I actually just did linear functions a few minutes ago. Those are degree 1 polynomials. They just look like mx plus b. Ignore all that. Mx plus b, well, it's a1 is m and a0 is b. But what about degree 2 polynomials? Well, they're called quadratics. And they're normally written as ax squared plus bx plus c. So that's a quadratic function of x. It's a special case of a polynomial. Okay, so the things that we have to say about quadratics, there is a thing called a discriminant, and that's going to be very important. And write that as delta. It's b squared minus 4ac. Okay, you've seen that before. In fact, the solution of the quadratic equation, the solution is that x is equal to minus b plus or minus the square root of that discriminant over 2a. Of course, you're taking the square root of something, so that only makes sense if the something is not negative. And in fact, what you'll find is you get two solutions if the discriminant is positive. You get one solution if it's 0. That's because the square root is then 0, and plus or minus 0 is still 0. And you get no solutions. Man, this chalk is just disintegrating. No solutions if the discriminant is negative. Okay, so that's why it's called the discriminant. It discriminates between these three different cases, depending on whether it's positive, 0, or negative. Okay, so that's just the quadratic formula. You all know that. In fact, in the case where the discriminant is 0, you have a double root. There are sort of two solutions, but they're the same. It looks like one solution, but it's actually a double root. Anyway, there's one technique that you need to know. You don't need to know it this week or next week, but soon you're going to need to know it. And it's completing the square. I know, it's no fun, but you need to know how to do it. Okay, I'm just going to show you by example how I complete the square. So my example is going to be, I'd like to complete the square on that. Okay, so what that basically means is I want it to be something squared plus a number. Okay, so rather than get bogged down in definitions of this, let me just do it and show you the idea. So the first thing is I hate the 2 out the front. I want this to be a 1. Okay, that would be called monic if the leading coefficient, the very first coefficient of the highest degree term is 1. That's called monic. So I hate the 2. I'm just going to take it out as a factor. 2 x squared minus 3 halves x plus 5. Okay, so what I'm going to do is leave a space and come back and write the final answer there. I'm just going to work with the nicer one x squared minus 3 halves x plus 5. Okay, so how am I going to complete the square? Well, I keep the x stuff. Basically, all I'm going to do is fiddle around with the constants. So I'm going to take this number here, minus 3 halves. I'm going to halve it. So the key number is minus 3/4. That's half this coefficient of x. So what I'm going to do is square this to get 9/16. And I'm going to wishfully write 9/16. So I've halved it, I've written that down as the key number, and then I'm just squaring it. Now, of course, that's a load of bull. What I've just written is total bull. So how do we fix it? Well, first way to fix it is to, again, take away the 9/16 and add back 5. Okay, so no one can quarrel with that. You might wonder why the hell I would do it, but hopefully that will become clear. But certainly that's true. Well, the reason I do it is because this immediately collapses into x plus, in this case it's going to be minus, this critical number, all squared. That's that piece. If you don't believe it, multiply it out. You get x squared plus twice this times this, so it'll be the minus 3 halves x plus that squared. Okay, so mentally you can see that that reduces. And then all you have to do is a bit of bookkeeping at the end to see what is 5, or minus 9/16 plus 5. Well, 5 is equal to 80/16, so this is going to be 71/16. And that's completed the square of this beast here. And now all I have to do is multiply the whole thing by 2 and maybe simplify it down to 2x minus 3/4 all squared plus 71/8, which I hope agrees with what I've written in my book. Okay, so that to me is the effective way of completing the square. Of course, as I said earlier, there are other methods or tricks or whatever, but I love this idea of just adding on what you need, then fixing it up, and then putting in the original, and you can see exactly how to group these things. Okay, any questions about that? As I say, we don't have to do it right now, but eventually you're going to have to do this, so might as well learn it. Okay, so the other functions in our ingredients list, very quickly, are rational functions. And they look like p of x over q of x, where these are polynomials. So we're going to be dealing with rational functions. We're going to be dealing with exponentials and logarithms. Okay, well, we're going to be talking a lot more about them soon. They look like 2 to the x or 2 to the minus x, log x base 2, and of course that you can replace the 2 by some other base. Now, in the book or notes are graphs of a lot of these things, but let me just, and I don't have time to go through them, let me show you the graph of exponentials and logarithms. It turns out it doesn't really matter what the base is. As long as it's bigger than 1, it looks something like this. Y equals b to the x. As long as b is bigger than 1, they all go through 1 here. They have a horizontal asymptote down at 0 on the left-hand side, and they just go rapidly up to infinity. There's no vertical asymptote there. So it's really useful to know. If we draw in a mirror line, this satisfies the horizontal line test, so there's actually an inverse function that looks something like this. And there's a vertical asymptote here where there was a horizontal asymptote there. And this is actually log x base b. It's the inverse function of b to the x. And we're going to be doing this in great detail. But I just thought that you should see the graphs of these two things. It doesn't matter, as I say, what b is as long as it's bigger than 1. Of course, the shape changes a little bit, but it just becomes steeper or flatter, but the general shape looks very similar. Okay, so there's trig functions, which I'm going to talk about very soon. The only other thing I want to talk about first is a little bit about absolute values, because these things can be really tricky. Okay. Here's the deal. When you see absolute value of x, you should convert it to a piecewise defined function. You should think of it as being x when x squared is greater than or equal to 0, or minus x when x is less than 0. Do you believe it? What's the absolute value of minus 3? Well, according to this, it's negative 3. So it's positive 3. When x is negative, actually minus x is positive. So this works. Okay? So that's one thing I have to say about absolute values. Here's another. If you look at that quantity, this is the distance between x and a on the number line. Okay? So what is this set here? Let me be consistent here. Which numbers satisfy this inequality? Absolute value of x minus 1 less than or equal to 3. What is that set? Well, there's two ways of doing it. I'm going to use these two things here. These two different ideas. So first idea, what is the absolute value of x minus 1? Well, what you've got to do is take that formula. There's 5 times x appears in it, and every single time I'm going to replace it by x minus 1. Okay? So this is actually equal to x minus 1 if x minus 1 is greater than or equal to 0, and it's equal to negative x minus 1 if x minus 1 is less than 0. So it would be cleaner if we rewrote this as x minus 1 if x is greater than or equal to 1, and negative x plus 1 if x is less than 1. And that immediately tells us how to graph it, by the way. It just says, look, when we're to the right of 1, it looks like y equals x minus 1. So that's this line here. But when we're to the left of 1, it says it's negative x plus 1. Well, that's a line of slope minus 1 with y-intercept 1. So it's this. So there it is as a piecewise defined function. Of course, going on what I said before, you can also think of this as the same as the graph of just absolute value of x, but shifted over by 1 to the right, because we've replaced x by x minus 1. So anyway, to see where is it less than 3, well, we need x minus 1 has to be less than or equal to 3 if x is bigger than 1, or minus x plus 1 has to be less than or equal to 3 if x happens to be less than 1. And in the first case, you'll see that x is less than or equal to 4, provided that it's bigger than 1, bigger than or equal to 1. And in the other case, x has to be bigger than or equal to minus 2, at least as long as it's less than 1. And if you combine the two, you do get all of this stuff. So you'll get minus 2 less than or equal to x less than or equal to 4. But the easiest way to do it is just to say, oh, take 1. X minus 1 absolute value is the distance between x and 1 on the number line. So which points have distance no more than 3? Well, we'll set our compass at 3, and that takes us out to 4. Or we go backwards 3, and that takes us down to minus 2. And so the answer is that all the x that satisfy this are the same as just the interval negative 2 to 4. Okay, so don't be scared of absolute values. Convert them to piecewise defined functions using that, and you have to change all 5 x's. Okay, and before I move on to trig, what is the graph of x minus 3 over the absolute value of x minus 3? What does that graph look like? Well, it looks like a nasty function, but it's actually not so bad if you use this whole definition here. You see, the absolute value of x minus 3 is equal to, by the same sort of logic, it's equal to x minus 3 or negative x minus 3, depending on whether x minus 3 is greater than or equal to 0 or less than 0. And of course, this is the same as saying x greater than 3, and this is the same as saying x less than 3. So if you plug that in, this means that y is equal to x minus 3 over x minus 3, which of course is just equal to 1, provided that x is greater than or equal to 3. Actually, can x be equal to 3? The denominator would then be 0. So actually, we'd better get rid of x cannot be equal to 3. We'd better get rid of that. In the other case, it's negative. So actually, the negative's on the bottom, to be more precise. But it still works out to be minus 1 if x is less than 3. So we're ready to draw the graph. The function is just equal to 1 to the right of 3 and negative 1 to the left of 3. And it's not defined at 3. 3 is not in the domain. So there's the graph of this. And it would be the same if the absolute value was on the top as opposed to the bottom. Doesn't make a difference. Try it and see if you don't believe me. All right. Are there any questions about any of that stuff? If you have one, just shout it out as I erase all this. Have you all seen all this before, basically, but just getting it back in? Or is there anything new? I'm just curious. Anyone seen anything new tonight so far? Okay, but it's good to review these things. And we'll certainly be doing new stuff next time. All right, trig functions. That's the one type of function that I did not yet talk about. And we've moved on to chapter 2 of the book. Okay, so trig functions. Here's one thing. You've got to use radians. Okay? No more degrees. Got to use radians. Okay, so you've got to be totally comfortable with the idea that 90 degrees is pi over 2. And it helps to be able to deal with things like, 5 pi over 4. I mean, here's the thing. You should be able to draw a little picture and see where it is. We're going to go 0. We're going to put pi over 2 here. That's 90 degrees. If we go around another 90 degrees, that's pi. If we go another 90 degrees, we get 3 pi over 2, and then back to 2 pi. So this is going to be a very useful diagram. It's like a quadrant diagram. So where's 5 pi over 4? Well, that's 5 quarters, which is halfway between 1 and 3 halves. So this angle here, starting at this positive direction, going around, is 5 pi over 4. Okay, so what is that angle? Well, at 180 degrees, that's 270 degrees. So this would be 45 degrees more. So I guess it's 225 degrees. Now in the book, at the beginning of chapter 2, there's a diagram of all the common angles that you should try to be flexible and, flexible. You should try to learn it. I'm not suggesting you memorize it, but you should be comfortable with it. But in case you forget, here's a nice little formula. Angle in radians is equal to pi over 180 degrees times angle in degrees. That could be useful if you have trouble remembering. So, for example, we know 5 pi over 4 was our angle times angle in degrees. And so the pi's will cancel out. And so our angle in this case is 5 quarters times 180 degrees, which works out to be 225. Okay? So there's a useful little formula. Now, we all know sine, cosine, and tan. Just to remind you, if it's between 0 and pi over 2, Well, you've seen this before. There's an angle theta. We've got the opposite, we've got the adjacent, and we've got the hypotenuse. Of course, if theta happens to be over here, the hypotenuse is still the same, but the opposite and the adjacent are switched. Opposite, of course, is opposite the angle, of course. So, anyway, I'm saying nothing new. Of course, you know your SOHCAHTOA, that sine of theta is the opposite of the hypotenuse, and that your cosine of theta is your adjacent over hypotenuse, and your tan theta is equal to the opposite over the adjacent. Okay, so obviously you've got to know that. Something you may not use so much before, but we're going to be using an awful lot of them, are the reciprocals of these things. So cosecant, you've got to know, is 1 over sine. Secant is 1 over cosine. And cotangent is 1 over tan. Okay? So you've got to know those. Of course, you can change this to hypotenuse over opposite if you like, but it's better to think of them as just the reciprocals, I think. Okay. Now, before we do angles that are bigger than pi over 2, or less than 0 for that matter, there are some really common values that come up over and over again. And here's a little table. Now, see, calculus isn't about memorization, but there's just a few things that you really, really should know. So here, I think, is a totally vital table to know. It just has some of the common angles here. Pi over 6, pi over 4, pi over 3, and pi over 2. That's it. So I hope that you should be able to just fill this in without thinking. I'm just going to write it down because it's not particularly exciting. But at least if you've got the top row, the second row is just the reverse of it. So cosine pi over 2, cosine 90 degrees is 0. Tan, of course, is just this divided by this. And it works out like this. But unfortunately, I can't take 1 over 0. Tan of 90 degrees, tan of pi over 2 is undefined. So I'm going to put a star. Okay, when I say you have to know this table, sure, you could just write it out at the beginning of a test or something like that. Fine, but it's really good to know what's cosine pi over 3. 1/2. Okay, that's the level I want. How about tan of what is 1 over root 3? What's inverse tan of 1 over root 3? Well, pi over 6. So I'm asking you to learn it 2 ways. And believe me, it could be, I think it would be very useful if you don't know them at the drop of a hat, to put them on flashcards. There's not a lot, right? There's 15 if you go this way, or there's 15 in the inverse. So 30 flashcards. Actually, you don't need the reverse of the star. So there's like 29 flashcards, and you just pick one up and say, what is it? And then look at the answer at the back. That would be useful. Okay, it's not very exciting, it's not very interesting, but from an exam point of view, it's very useful. Okay? So, that's the very, very basic thing. On the other hand, what about something like this? What is sine of 7 pi over 6? Well, if you actually draw this, it's bigger than pi. We can't really draw a right-angled triangle with an angle that's 7 pi over 6. It's just too big. So what we have to do is go back to our original diagram there. Again, 7/6 is a little bit bigger than 1. So 7 pi over 6 is actually going to be over here. So I'm going to label that ray. What I really mean is that this angle here, and again, just to orient ourselves, that angle, starting here and going around counterclockwise, is 7 pi over 6. Okay, so I label this instead of the angle because it gets messy when you want to make lots of different angles there. So what should the sine be of such an angle? Well, you pick any point on this line, it doesn't matter. I'm going to drop a perpendicular. All the triangles that I could come up with in this way are similar to each other, so ratios are the same. what I'm going to do is take the opposite here over the hypotenuse. Well, the hypotenuse is always going to be positive by convention. But here, look, the opposite is actually below the x-axis, so it's negative. It's like a negative number on the height of it is negative. So the sign of this should be negative. It should be a negative number. So, whereas if you were up here, the sign would be opposite over hypotenuse. The opposite is positive, and the hypotenuse is always positive. So sign should be positive anywhere here and negative anywhere down there. Interesting. Okay, so how do we deal with this? Well, what we do is we take this little angle in here. It's called the reference angle. Well, we needed 7 pi over 6, but this is only pi here, so the difference leaves us with pi over 6. That is the reference angle. So basically, the reference angle is the closest angle between the ray you're dealing with and the x-axis. So if you're in here, the reference angle looks like this. If you're over here, this is the reference angle. If you're here, the reference angle goes up like that. And if you're down here, the reference angle would be up to the x-axis like this. So by drawing a picture, you should identify the reference angle. And then that's going to be the same as sine pi over 6, because that's the reference angle. The only difference is you might need a plus or a minus there. But as I described, because the opposite is negative, you actually need a minus. So plus or minus, which one? Minus. So it's minus sine pi over 6, which from our table, there it is, sine pi over 6 is a half. So sine 7 pi over 6 is minus a half. Okay, so that's a sort of introductory example. There's actually a nice way to know whether it's plus or minus, and it's the so-called ASTC. So I'm going to explain what that is in a few seconds. Do a few more examples, and then we'd better look at some graphs and some trig identities, and then I think that will be it for this lecture. Review session. All right. So, 4 useful letters. ASTC. Probably seen that before. In Australia, we learnt this as all stations to Central, because Central Station was the big station. It's probably a British thing. I have no idea what you guys might have learnt for that. Yeah. All students take calculus. So what happened, so I guess this is for pre-calc, right? And it may not be true. Could be a lie. But everyone in this room is taking calculus. So maybe it was supposed to be motivational. Anyway, what does it mean? Well, it means that all trig functions are positive. All positive here. Sine, cosine, tan, they're all ratios of positive numbers. Well, here it means only sine is positive. I sometimes write plus VE to mean positive. Tan and cosine are negative. Of course, I say only sine. Clearly, cosecant is the reciprocal of sine. That's going to be positive too. So out of the 3 major trig functions, sine, cosine, tan, only sine is positive. Why? Because when you're here, the opposite is positive, but the adjacent is negative because it's negative x-axis, and the hypotenuse is always positive. So if you look at those ratios, sine is positive, cosine is adjacent, is negative, so that makes that ratio negative, and the tan is opposite, which is positive, over adjacent, which is negative. So again, that will be negative. And you can chase this through the other quadrants as well and see that tan only is positive, the other's negative, and cosine positive here. That one's a little bit interesting. When you're down there, actually the tan is the interesting one. Both the opposite and the adjacent are negative, but the ratio of negative to negative is positive. So that makes tan positive there. So what? Well, it makes it really easy to find certain things like this. Suppose we wanted to deal with, say, cosine 7 pi over 4. Let's just take a look. First thing to do is draw a picture. Where is 7/4? It's between 3 halves and 2. This 0 and 2 pi are basically the same thing as far as the angles are concerned. So what do we do? Well, it's going to be here. The reference angle, well, that's going to be pi over 4, because 2 pi minus 7 pi over 4 is pi over 4. So this is going to be the same as cosine pi over 4, and you just have to decide whether it's plus or minus. Well, it's plus because we're in the fourth quadrant, and that's the quadrants are labeled 1, 2, 3, and 4. So the fourth quadrant, cosine is positive. So it's equal to plus cosine pi over 4, which from the table and hopefully our memory is 1 over root 2. How about this? What is tan of 9 pi over 13? Well, we can't simplify it that much, but we can get some grip. 9/13 is between 1/2 and 1. So we're going to be somewhere in here. 9 pi over 13. So the reference angle is going to be over here. It's going to be 4 pi over 13. Why? It's just 13 pi over 13 minus 9 pi over 13. So the difference is 4 pi over 13. So the best we can do with this is say that it's plus or minus tan 4 pi over 13, which at least we can understand in terms of a regular triangle, right angle triangle. And is it plus or is it minus? Well, this is the S here. S is not tan. S is sine, so it's got to be minus. So here's our little calculation. I don't know how to simplify tan of 4 pi over 13, so I'm just going to leave it like that. Okay, so it's really, really important that you're able to deal with all these sorts of unusual angles. And they can get even more unusual. They can go outside the region 0, 2 pi. So we're well into section 2.2 here. In fact, it gets labeled 2.2.2. What if you're outside 0 to 2 pi? Well, the technique there is to subtract multiples of 2 pi or add multiples of 2 pi until you get into the nice region between 0 and 2 pi. So, for example, if you have to work out secant of 15 pi over 4, how do you deal with that? How big is 15/4? It's bigger than 2. In fact, we can knock off 2 of 15 over 4. What happens if you knock off 2 from 15 over 4? What do you get? 2 is how many fourths? Right, well, so 2 is 8/4, so I'm going to knock off 8/4, and this is the same as secant 7 pi over 4. So I knocked off 2 pi. Why is that legit? Well, here's 7 pi over 4. How would I get 15 pi over 4? Well, you go all the way around and around and around. So that's 15 pi over 4. If you think about it, it's a little bit less than 4 pi, 16 pi over 4. 4 pi would be 2 complete revolutions. But of course, you're still facing the same direction. So as far as angles are concerned, 15 pi over 4 and 7 pi over 4 are the same angle. They're not the same number, but they are the same angle, because all you're doing is just getting dizzy going around a few more times than you need to, but you still end up pointing at the same direction. So anyway, this actually is 1 over cosine 7 pi over 4. And we just worked that out, actually. Cosine 7 pi over 4 was 1 over root 2. We just saw that. If we hadn't already done that work, we would have had to do it anyway. But since we've already done it, we get root 2 as the answer without too much ado. How about sine of minus 5 pi over 6? What does that mean? Well, in order to get the minus, well, to get plus, you go around counterclockwise. So to get minus angles, you go around clockwise. So we're actually going to go around to 5 pi over 6, which is, so this is minus 5 pi over 6. It's sort of 5 pi over 6 would be up there, but we're going to get the mirror image of that in the x-axis. So, of course, this is the same thing as plus 7 pi over 6, as you can see by adding 2 pi on. If you add 2 pi to negative 5 pi over 6, Well, 2 pi is 12 pi over 6, and minus 5 plus 12 is 7. So you see 7 and 5 together make the 12 pi over 6. And sure enough, this is exactly the same as sine 7 pi over 6. Now that gets us between 0 and 2 pi, and we can work it out. And in fact, that was the first example that we gave, and that was minus a half. Okay, so again, we're not going to need this trig stuff immediately, but as we go on, you will find, especially, towards the end of the course, you're expected to know all this stuff and be able not to get bogged down. Believe me, there's enough trouble with calculus, with derivatives, integrals, all this stuff we're going to do, so that this pre-calc stuff has got to be solid. You have to be really, really good at it. So if you have any spare time, just try to write down. You can just take any multiple of pi over 4, over 3, over 6, and you can just find the sine, cosine. It could be a big multiple. You could say, what's secant of 75 pi over 4? Or 78 pi, 77 pi over 4, something like that. Just work it out. You can do it. Just knock off enough 2 pi's until you get down to between 0 and 2 pi, then use the ASTC method. Okay, time is running out, but we still have a little bit. Are there any questions about what I've just talked about? I know I'm doing a lot of talking here, but you can do some too if you have a question. Okay, well, I really only have 2 more things to discuss. And one is the graphs of the trig functions, which I think you should know. And then I want to go over the trig identities that we're going to need throughout the course. And that will complete what I think is really all the pre-calc that you actually have to know. Of course, you need to know how to expand and factor things, but I'm not going to talk about any algebra here. Okay, so let's just draw the graphs. These are all in the notes book, so you don't need to draw them accurately, but it's really good to know how to draw these things. So first of all, you're probably used to drawing them like this. No. If you're going to draw them to scale, it's actually more like this. See, pi comes here, 2 pi is here, and the height is only 1. Pi is about 3, right? 3.1415, and so on. So this should be 3 times as long. Of course, this should be 3 times as long as that. Of course, when you're dealing in degrees, it doesn't really matter, but in radians, they're numbers, and you should try to get the scale right when you can. Okay, so this is pi over 2. This is 3 pi over 2. And as I said, angles are the same when you add 2 pi. So, of course, the graph has to repeat. This is called periodic. So it has a period of 2 pi, and it repeats. Okay, so by the way, this is the best way of finding sine of pi, or sine of 3 pi over 2. There, the angle method doesn't work so well because you're not really in a quadrant, you're on one of the axes. So I would say for sine or cosine or tan of a multiple of pi over 2, or pi for that matter, use the graph. The graph is really helpful. So, for example, what's sine of 3 pi over 2? Well, either you know it or you don't, but even if you don't, and you can just draw this graph with those main signposts, you can see that the answer is -1. Just read it off the graph. It doesn't help you find the sine of 7 pi over 5, because that's not clear how high that is, or anything like that, but, for these ones, you should use the graph. Okay, by the way, while we're looking at it, what's the range of sine? What's the range of this function? The domain is everything. You can keep going forever. What's the range? -1 to 1 inclusive. So it's worth noting that. How about the symmetry? Well, does it look like an even function? Does this look like a mirror for the function? No. Does this look like a point symmetry? Yes. It's a 180-degree point symmetry. If you pick all this up and rotate it, it will overlap that part to the left there. So sine is actually odd. And that leads us to our first little identity, which is pretty useful to remember. Won't come up that much, but certainly can't hurt. Okay, remember, for an odd function, f of minus x is minus f of x. So, of course, sine of negative x is negative sine x. And by the way, it's a good exercise to check that that's consistent. Here we worked out sine of negative 5 pi over 6. That's the same as negative of sine 5 pi over 6. So if you didn't want to do it with 7 pi over 6, you could do it with 5 pi over 6 in the second quadrant. And check that that works. You should check that that's the same thing. Okay, so let's quickly knock off the graphs. I won't spend so long on the others. We'll do the graphs of I'll just do cosine and tan and refer you to the notes or the book for the other three. The secant and cosecant. This chalk does not erase very well. Apologize. Okay, so cosine really quickly. Again, try to space it out properly. Between 0 and 2 pi, we start at 1 this time. So it's just like sine, but it's shifted over. So you'll find and so on. So again, it's periodic and so on. And there's a nicer picture of it in the book. So what's cosine of 3 pi over 2? Let's read off the graph, 0. Okay. By the way, is cosine even or odd? It's even. Cosine is even. Cosine x and cosine minus x are the same thing. Okay? That's a mirror symmetry there. So it's useful to know that. And let me just do tan, because it's quite different. The range of cosine is also minus 1 to 1 inclusive. Tan, on the other hand, is the ratio of sine and cosine. And it's based like this. It actually has vertical asymptotes, and its range is everything. All numbers. It's already covered all numbers. Unfortunately, its domain is not everything. Minus pi over 2 is not in the domain. Pi over 2, odd multiples of pi over 2 are not in the domain of this. And it, again, is periodic. It has intercepts at multiples of pi. So 0 pi, 2 pi. Here's an asymptote at 3 pi over 2. Here's an asymptote at 5 pi over 2. And that just keeps on repeating. Well, that's really pathetic. And so on. And again, there's a nicer graph of it in the book. This is also an odd function. It's also odd. As you can see, it's 0 is the point symmetry. So tan is odd. Tan negative x is negative tan x. So tan and cosine, tan and sine rather, are odd functions, but cosine is even. So, as I mentioned, there are some vertical asymptotes. What's the periodicity of tan, for that matter? Sine and cosine repeat every 2 pi. This one repeats every pi. Of course, it also repeats every 2 pi, but you can do better. You can say it repeats every pi. And that is because of the ASTC. You see, sine goes plus, plus, minus, minus. So that's the best you can hope for. Before it gets to plus again, it needs to go all the way around. Same cosine is plus, minus, minus, plus. But tan goes plus, minus, plus, minus, plus, minus. It repeats after just 2 quadrants. So that's the pi that we're seeing. You don't have to go all the way to 2 pi. Okay, so that's the graphs. As I said, please check out the book for the other 3 graphs. It's worthwhile knowing them. But, of course, they come straight from these three graphs since they're just the reciprocals. So, the only thing I have left to say in the last 10 or so minutes is that I wanted to go over some of the trig identities that are very, very useful. And this is all in section 2.4. So the first sort of obvious identities, I mentioned that tan x. I've said this earlier actually right at the beginning, but it's worth noting that tan is sine over cosine, because sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and the hypotenuses cancel out. And you get that. And of course it's useful to know that cotangent of x is cosine x over sine x. Okay, so those are sort of basic trivial identities. Now here's a really important identity that is going to come up over and over and over and over again, and you've seen it before. It's actually Pythagoras' theorem in disguise. Cosine squared x plus sine squared x equals 1. And I should just mention that it's not just true for x, it's true for whenever these two match. Cosine squared of a watermelon plus sine squared of a watermelon would equal 1 if I had any clue how to take the sine or cosine of a watermelon. But you get the idea, right? This could be 7x squared, as long as that 7x squared is. If they match, the sum of the square of cosine squared and sine squared of that quantity is 1. Why is it Pythagoras' theorem? Well, if you take a triangle of side, a right angle triangle of side 1, then this length here, y, is actually sine x. In fact, sine x would be y over 1. And x is cosine x. And of course, x squared plus y squared is 1 squared by Pythagoras' theorem. And that's just cosine squared plus sine squared is 1. So it's nothing, it's just a trigonometric way of saying Pythagoras. Now, if you divide this equation by sine squared, actually let's divide it by cosine squared first. Well, you're going to get 1 over here. You'll get sine squared over cosine squared. That's the same as sine over cosine all squared. So that's just tan squared x. Whereas 1 over cosine squared, well, that's secant squared. If you look back, secant is equal to 1 over cosine. So that's what you get. I mean, I said that pretty quickly. You can check the details if you like, but you should know that like the back of your hand. If you instead took the original equation and divided by sine squared x, you get a slightly different version. You get here cotangent squared x plus 1 equals cosecant squared x. Again, a useful identity, although I have to say that these two seem to come up a lot more than that one. That's sort of the poor cousin. I think I can get away with this bottom board for the rest of the identities. There aren't a lot more. Now that might be a little bit optimistic. Next week, I'm going to get some better chalk. This chalk is fine until you try to erase it, and then your arm falls off. Oh, man. I'm not ambidextrous, which is a pity because... Okay, not much longer. 2 more classes of identities. What do I want to say? I want to say cosine of pi over 2 minus x is sine x. That's reflecting the symmetry of the graph, the fact that one is basically slid over from the other. See, the idea is that when you say cosine x, that's actually short for complementary sine. Complementary doesn't mean nice. In this case, it means adding up to 90 degrees, and pi over 2 is 90 degrees. So here it is, x and pi over 2 minus x add up to pi over 2, so they're complementary angles, and the cosine of one is the same as the sine of the other. And the same is true if you change cosine to cosecant and secant, or cotangent and tangent. All these are written out in full in the book. It's actually true if you write cosine here, as long as you write sine there. You see, cosine is actually sine. Complement of the complement is the original. And of course, you've got the other two as well, and I refer you to section 2.4 of the book for all those written out. And then finally, there's a class of formulas that look like sums and products, and they're not going to come up very often, but a special case comes up all the time, and I'll draw your attention to that. It's useful, but not critical, to remember how to expand sine A plus B. This is sine A. Oh, man, I can barely even read it. This is sine A cosine B plus cosine A sine B. And actually, if you happen to have a minus there instead, you can put the minus there. So that's actually a pair of formulas written as one, to be brief. Cosine A plus B is actually cosine A cosine B. See, the sine one mixes them up. You get sine cosine plus cosine sine. Bless you. Whereas the cosine is more homogeneous, as it were. Cosines, then the sines. But there's a minus in between. And that means that if you're going to have a minus there, you actually have to have a plus there. You end up with this weird thing, minus, plus. Anyway, the special case of these two is when B and A are the same and you're dealing with sine of 2A and cosine of 2A. And those are the ones that I really think you should learn. And because the board is so hard to read, I'm actually going to come over here. They'll all fit up here. Sine of 2A, if you actually use that formula there, it works out to be 2 sine A cosine A. Whereas cosine 2A, there's two forms that are useful. One is 2 cosine squared A minus 1. And because you've got a cosine squared, you can use that Pythagoras' theorem identity over there. And you can also write this as 1 minus 2 sine squared A, as it turns out. So these are essential. Those are very important. As a little example, I'll give one example, and then I'm done talking for the time being. How would you reduce sine of 4x down to just sines and cosines of x? I don't want the 4x, I just want to deal with x. Well, 4x is 2 times 2x. So let's use this top identity here, but with A replaced by 2x. So it's going to be 2 sine 2x cosine 2x. Now I've got to use the identity twice, one for each factor. So this one is 2 sine x cosine x. That takes care of this beast. As for the cosine 2x piece, I could pick either one. Let's just pick the first one. 2 cosine squared x minus 1. And you can simplify it a little bit if you really want to. You could multiply it out and write 8 sine x cosine cubed x. And the other term will be minus 4 sine x cosine x. And that's not the only way you can write this. I could have chosen the other identity there. There's even a third one, but I'm not going to bother writing it. So in any case, that is one way of simplifying it so that everything is in terms of x. So there is my 2-hour everything you need to know about pre-calc. Are there any questions? We have a few minutes, and then after we finish this, you're welcome to come up and ask me about homework problems. I'll try to finish a little earlier in the future so that the lectures don't last the full, or the review sessions lecture part doesn't last the full 2 hours, and you can ask questions. So anyway, on the video, until next time, and now that we've, sorry, cut, cut. So, have any questions that they'd like to ask about the homework or anything like that? And you're all welcome to stay or leave, of course, as you want, but go ahead.